Welcome to the episode 5 on distributed systems. Today we are going to talk about how do we achieve coordination and the consensus between nodes in distributed systems. So first let's take a look at the why consensus and coordination even matters. So let's say that we have multiple nodes and we need to manage the state. We need to manage that we need to make sure that they agree on the single truth, even if the sum of the nodes are failing. So what's that mean? For example, let's take this example. Let's say we have three nodes, A, B, and the C, and each instance of our application, right? And they may have a different values, but what we need to make sure is we need to make sure that each of these nodes have the same value, right? Otherwise, our system is inconsistent. So what we do is on node A and the B, they are proposing their values, so they are proposing their value and they are agree on the one value, right? Let's say even A proposed 5 and the B proposed 11 based on certain algorithm. We are agreeing on one value. Let's say that during that voting moment, a node C is not available. Even if the node C is not available, then in that node B and the A and the B decide what the value should be, and that value also is propagated to the node C. So analogy for that, for this example, would be that let's say that we are 5 friends and we are deciding a dinner location. Even if the one of our friends' phone dies, in that case we must agree on certain location, right? The same is here. So let's say that we have 3 nodes or 3 friends, and let's say in this case C is not available, right? Node C is not available, or friend or one of the friends is not available. But anyway, the remaining friends are agree on the value, on the location, and once the another node or another friend is available, then that friend can also accept the value, or accept in case of the deciding the dinner location, accept the address of the venue. So let's take a look at the consensus problem. Right? So what are the requirements for the consensus? The first requirement is that when we are agreeing on the value is that agreement itself. So what it means? It means that all correct nodes choose the same value. So for example, in this case, if we are choosing the value 5, let's say node A and B, they are agreeing on certain value and they have selected the value 5, then the all nodes should accept that value. The second one is that the validity. So what's that mean? That the chosen value was proposed by some node. So which means that that value doesn't come from somewhere, it is proposed by one of the nodes, right? So we have certain algorithms how we can exactly decide that which node proposes and which nodes accepts the value. But the point being is that that value that we are choosing, that it should come from certain node. Another one is the termination. What's the termination mean? Termination means that every node eventually decides. So it means that let's say we have in this case, right? Again, let's take this example. We have 3 nodes, and the one of the node at the time when the decision is made, that node is not available because of the network issue or some other issues. But eventually, that node also decides. That node also accepts that value. And the last one is that the integrity. So it means that the decision once made, it never changes. So what it means in this case, in our case, let's say that the nodes agreed on the value 5 and they are accepting that value. So that value cannot be changed. Even let's say a node at later in time, because of the certain logic, wants to change that value cannot be changed because that value should be the same across all of our nodes. So what are the challenges in the consensus? The first one is that the asynchronous network, so there is no global clock. About the clock problem, we have talked in our previous episode, so why having the consistent clock is important in distributed system. Another one is the message loss, the duplication, receiving duplicate messages, and the reordering, and also the node failures and the partition failures. So what are the algorithms? So we have in general, we have reviewed that how in a general sense, we are choosing we are making sure that all nodes have the consensus on certain value, but how exactly we are doing that, we are using one of these algorithms. Either we are using Raft, or we are using Paxos, or we are using Zap, or similar algorithms. So that is how we are achieving the consensus, and what are the requirements for the consensus. Now let's take a look at the leader election basics. To maintain order, systems elect a leader node. So for example, let's take this example. Let's say that we have a nodes A, B, C, D, and what they do is each nodes, they are exchanging the heartbeats. And how we usually elect a heartbeat is that the highest ID alive is selected as a leader. So what are the responsibilities of the leader node? Leader node coordinate writes, maintain term, and detect the failures, and after that it triggers the re-election. So we are guaranteed that the only one leader active at any time. So now let's go and see that the exact implementation for the two algorithms, two most widely used algorithms in the consensus in distributed system. The first one is the Paxos, is a classical consensus algorithm. So what it's about? So for each node, each node has either one of these roles. The node is either proposer, or it's which means that it proposes the value, as we have seen earlier, right? So we have, let's say, nodes A, B, and the C. So they are proposing value. We have acceptors, they are voting on the proposal. So they are not proposing any value, but they are just voting. And also learners, they are just learn the final decision, so they accept the value. So what are the phases? In general, we have the two phases. The first one is that the prepare and the promise, right? So, and we are ensuring that there are no conflicting proposals. So what's that mean? Let's say that we are proposing again the value 5, as we have seen in our previous example, right? So we get the promise from all the acceptors that they will accept the value. And after that, what happens is that all the nodes accept the value, and so majority accepts the value. Then after that, we are accepting that this value is accepted by all the nodes. So what's the guarantee here? That the guarantee here is that the one value is chosen by the majority, and it's a final. So it follows all our 4 principles, right? Then after we select the value, that is the agreement, which means that that node, that value is it should be all across all of the nodes. It's a valid, so it means that it should be proposed by one of the nodes. It's a terminal, which means that all nodes eventually should receive that value, and we also maintain the integrity, so which means that that value cannot be changed. That value that has been accepted by all the nodes, it will not be changed in the future, or based on some logic in one of the nodes. So where it's used in the system, for example, such as Google Chubby, in the Cassandra internals, and in the legacy systems. Let's take a look at another algorithm, which is a Raft. Raft is basically, it's a simplified version of the Paxos. It has a strong leader design. So what are the roles in the Raft? The first role is a leader. Leader is basically, it handles all the requests. All the requests are going through the leader, and it also handles the local replication. The next role that we have is a follower. Follower is a passive role. It responds to the leader. So it responds to all the requests that leader receive first those requests, and then subsequently leader send those requests to the followers. Also, we have a candidate. It's a temporary role. During the leader election, the follower may become a candidate, and it may if the follower becomes candidate, it requests votes during the election. If the candidate that received the highest vote becomes the next leader. So what are the phases for the Raft phases, right? The first one, or functionalities in the Raft, the first one is the leader election. So what happens in the leader election? Leader election, when we're just starting a cluster, or that let's say that the current leader fails, then what happens is that each follower starts a timer, and after that, what each follower does is, if it doesn't hear from the leader, if it doesn't hear the heartbeat from the leader, it may become a candidate. After it becomes a candidate node, then it's a temporary, right? It's a temporary role. After a follower becomes a candidate, it receives it receives the vote from all other nodes. If it gets the majority, it becomes a leader, and after becoming a leader, that node, that candidate now, which become a leader node, it sends the heartbeat to other nodes to assert the leadership. The next one is that the log replication. So what log replication is so all the requests, they are going through the leader node. Leader node first receive those requests, and after that, leader node send that request to the followers. If the majority followers, they are confirming that they have received that request, and after that what happens is that the leader commits the entry and applies it to the state machine. And also followers from their side, they also save that entry on their side. And the next one is what we have is the safety and the failover. So what's the safety and the failover? Safety and failover is that if let's say that the leader crashes, that right? So after the leader crashes, for the safety part, after the leader crashes, what happens is that the followers stop receiving a heartbeat. It triggers the election, and the most up-to-date node, it wins, and the new leader picks up exactly where the old one left off. So what it means? It means that let's say that the old leader has already committed certain changes. The new leader will not overwrite those changes, but will pick up from where the old leader has left. So where the Raft is used, for example, in the Kubernetes, database or storage. Or it's used in the console, it's used in the Rethink DB or Cockroach DB, and so on. So let's take a look at the real-world example of these consensus algorithms. The real-world examples are probably the most widely used example is the Zookeeper, which is used for the electing the leader node in Kafka, for example, or other similar systems. So for example, let's take these four systems: Zookeeper and the etcd, which is the database for the Kubernetes, console, and the Chubby. So each of them are using the different consensus algorithm. For example, Zookeeper uses the ZAP. It's the algorithm for the Zookeeper. For the it's etcd, we are using Raft, and for the console we are using Raft. For the Chubby, Paxos is used, and they all have their own cases, right? Why they are using the specific cases, why they are using the consensus algorithms. For example, in the Zookeeper, we are mainly used that for the coordination. Also, we are using for the logs, and we are using for the registry. And in case of the etcd, we are using that for the Kubernetes state storage, basically Kubernetes database. And for the console, we are using for the service discovery, and for the Chubby, we are using that for the Google's log service. So the core takeaway is that the consensus is important in the distributed systems, consensus algorithms, and they are brain of the distributed systems, because we need to ensure that the single truth, single value across many machines. To recap what we have learned today, right? So we have the consensus, which is important in the distributed system. It's basically all the nodes in our cluster, they are agreeing on the single state, on the single value. So what are the processes that we have? For the consensus is the leader election, which is basically coordination mechanism, and we have different algorithms how to exactly what are the steps for selecting the leader. So two widely used algorithms that we have reviewed today, which is the Paxos, it's a theoretical foundation, and we have a Raft, which is more practical, which has a more practical use in the consensus engines, and they're more widely used. And also the real world example of the consensus is the Zookeeper, which is used, for example, in systems like Kafka or similar, or etcd, which is used as a database or as a storage for the Kubernetes. That's it. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.